That leads us up to another key theorem, not quite as useful as it was maybe back when I was in high school, but still a useful theorem. And it's also to help us to limit the number of possible zeros that we would have to consider for real zeros of a polynomial, especially with agreement with the rational zero theorem. And it says, let f be a polynomial, degree n greater than or equal to 1, real coefficients, and a positive leading coefficient. So if our function doesn't have a positive leading coefficient, we'll multiply through by a -1 and change it. Suppose therefore, suppose that f of x is divided by x minus c. Okay? So we'll use synthetic division, right? If c is greater than 0, and if both the remainder and the coefficients of the quotient are non-negative, that includes 0, then c is an upper bound for the real zeros of f. Now you say, well, what's an upper bound? Well, an upper bound is like the maximum that it could be for the zeros. So some people will say, well, how much do you weigh? Well, I'm somewhere between 170 and 180 pounds. So 180 would be my upper bound, 170 would be my lower bound. So in this case, we're looking not for weight, but for the zeros of the polynomial, so we can find an upper bound for it. Now, there are lots of upper bounds. We will probably try to find the smallest upper bound when necessary, because that way we limit, no pun intended, what our possible real zeros might be. If c is less than 0 here, and if the coefficients of the quotient and the remainder, this time not all non-negative, but they alternate in sign, positive or negative. And if you have a 0, it's either positive or negative, however you need it. So if you need it to be negative, you can consider it negative. If you need it to be positive, you can consider it positive. Then c is a lower bound for the real zeros of f. So remember, we'll be looking at lower bounds that are negative values. Now, what I have, and again, I'm emphasizing the polynomial function must have a positive leading coefficient, as I mentioned up here. So if I have one here in this first example, but if I didn't, I would multiply through by -1, and because it's going to have the same zero, whether it's a constant multiple of it or not, it'll have the same zeros. So in this first example, given f of x is equal to x to the fourth minus 2x to the third minus 13x squared minus 4x minus 30, look at all the possible rational zeros. That could be p, that could be q, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. There are a lot to check. It says, determine if 4 is an upper bound for the real zeros. Well, let's find out. I'm going to take 1, -2, -13, -4, -30, very conveniently that it's been written in descending order, no missing terms, and I'm going to start with 4. That's a 1, that's a 4, so far positive, that's an 8, -5. I can pretty much stop now. These are not going to be all non-negative because I have a -5. So is 4 an upper bound? No, it is not. Now you say, well, how would you find your lowest upper bound? Well, 4 doesn't work, so it can't be smaller than 4. I would go to 5, then I would go to 6, and I think it's actually 7 that's my upper bound here, if I'm not mistaken. I don't think 6 works. I think if you try this with a 7, well, let's just go ahead and try. I'll put it right over in a different color here. Let's say a 7 here. That's a 1, then that'd be a 7, then that would be a 5, and that would be a 35. And then that would be a 23, and then 7 times 23 is 161. Yeah, it's looking pretty positive right now. And 7 times that's over 1,000. So that's not gonna change the sign there. That's gonna be positive as well. So definitely 7. I'm pretty sure 6 gives me a negative somewhere, maybe the last term or so. But anyway, I would just progress through, starting with 1, working my way on up. Now in this problem, it said, is 4 an upper bound? So I went right to 4. Over here it says, determine if -4 is a lower bound for the real zeros of f. So what I'm going to do here, if it's less than 0 and negative 4 is less than 0, I'm going to divide to see if I get alternating signs. So I have 1, negative 2, negative 13, negative 4, negative 30, and I'm going to, if the quotient, the remainder alternate in sign here, so I'm going to put a negative, what did I just say it was? Negative 4 here. So that's 1, that would be negative 4, so that's negative 6. Alternating so far, that would be a positive 24, so if I add I get, what is that, 11, so it's still alternating. Negative 4 times 11 is negative 44, so that gives me negative 48, still alternating, plus minus, and negative 4 times negative 48 would be positive 196, so that would give me 166. And that's my remainder, plus minus, plus. So negative 4 is indeed a lower bound. Now, we are interested in the smallest upper bound. We would be interested in the greatest lower bound because these are negative numbers, so that we would, again, kind of limit what our possible real zeros may be. Now here we'll actually do this as we're finding zeros and their multiplicities. So what I'm going to do here is I want to consider P over Q. Now P over Q here, because P can be an integral factor of negative 18, Q has to be plus or minus 1, integral factor of the leading coefficient 1. I'm going to look at this and I'm going to say plus or minus 1 over 1, plus or minus 2 over 2, or over 1, plus or minus 3 over 1, plus or minus 6 over 1, plus or minus 9 over 1, plus or minus 18 over 1. And so I have some pretty good ones here. So let's find an upper bound so I don't have to go through all of these. So I'm going to go 1, 0, notice no x to the 4th, 6, negative 2, negative 27, negative 18. And I'm going to start with, as I mentioned, a 1. Now if I start with a 1, that's 1, that's 1, that's 1, that's 7, that's 7, that's 5, that's 5, and all of a sudden I hit a negative. Well, I can see that this is going to be not just barely a negative, this is going to be negative 22. So I'm thinking, not only is 1 no good, it's probably going to be a little bit bigger than 1, and not necessarily 2, but that's what I would do. I would go next to 2 and work my way through these until I can find 1, 2, 2, that's 4, 10, that's 20, that's 18, that's 36, that's 9, that's 18, and even though it's a 0, all positive, and I can use this as non-negative because of the 0. So this is kind of nice. I have an upper bound of 2. It's my smallest integral upper bound, and it's a 0. So that's pretty nice. So what I'm going to do next is take the depressed polynomial, 1, 2, 10, 18, 9, and I'm going to try 2 again. It can't be bigger than 2. I know it's not 1. It can't be 3, 6, 9, or 18. And I'm pretty sure 2 is not going to work because these are all positive. I'm never going to end up being able to get to 0, but I would go through 2. I'm telling you right now, it's not going to work. So now I'm going to find, if I can, a lower bound. So I would probably next go to negative 1. All right, so that's 1. That's, let's see, what do I have here? That's going to be, just a second here, I got to figure it out. That's going to be negative 1. That's 1. This is not going to be a lower bound. This is negative 1, this is 9, this is negative 9, this is 9, this is negative 9, but it turns out to be a 0. It's just not the smallest possible 0 that I might end up with. And fortunately for me, I have a depressed polynomial I believe I can factor. So I already have 2 of the zeros. I have 2 and negative 1. But now I'm going to take this guy here, I'm going to write him as x to the 3rd plus x squared plus 9x plus 9 is equal to 0. I'm going to use grouping. This is x squared times x plus 1. This is 9 times x plus 1. So I'll kind of bring it up here. I'm going to factor out the x plus 1, and that would leave me x squared plus 9. So I'm going to have x plus 1 equal to 0. I'm going to have x squared plus 9 equals 0. So if I subtract 1, I get a second 0 of negative 1. So I have multiplicity 2. Over here, if I subtract 9 and take the square root and take the absolute value and the plus or minus, I get x equals plus or minus the square root of negative 9, or x equals plus or minus 3i. So, find the zeros. My zeros are negative 1 multiplicity 2, 2, and plus or minus 3i. That's 1, 2, 3, 4, 5, and notice degree 5. So that matches up nicely. So the last couple of theorems and rules are mostly to help us in the process of trying to eliminate maybe some of the possibilities. As I mentioned before, not quite as useful because you could just pop out your graphing calculator. You could graph this, you could see where it crosses the x-axis, and you would have your limitations right away, your bounds and such. You would know how many are positive, how many are negative from Descartes' rule of science. But this is all very important information because these ideas are used in the proofs of other theorems that we're going to be studying, and therefore very important to the history of mathematics.